Alright, here in this video I'm going to try to keep it to 15 minutes. Is going to go over the answer key for chapter 6. 6.1. We've got a square root here. Square root of 121 is 11. This y to the 10th, remember this concept is all about the index and how many groups here you could take out. So with this being y to the 10th power, essentially we're dividing 10 by 2 here to figure out that 5 y's would make it out, giving us y to the 5th. On this one, cube root, perfect cube root of 8 take us to the 2. Once again, you can think of this as being here g to the 6th as g cubed and g cubed, right, to match that index of 3. So 1g makes it out, 2g's make it out. That's where we get the g squared. All right, on this one, square root of 25 is 5. You can really think of this as just a group of something to the 4th power, so that same group will be able to make it out 2 times after we square root it. Now, once that's out there, you would then FOIL this out. Remember, this answer is not x squared plus 4. That's wrong. It's this after you FOIL it out, and then you distribute that 5 through and get that answer. I put this one on here just to remind us if we're working in an equation standpoint and we take a square root, must have that plus minus. Same thing here, square rooting a fraction is simple. Square root the numerator, 11. Square root the denominator, 25. With a plus or minus, because it's an equation. Alright, this is one, you kind of think of it as a fraction if you wanted to, or use your calculator. Key component though, get that plus or minus. Take the 4th root, which you could also type in a number on your calculator and raise it to the 1/4 power if you are unsure about how to take a 4th root on the calculator. This problem here is just an evaluation problem. Temperature T in degrees Celsius of a liquid T minutes after heating is given by this formula. What's the temperature? When is the temperature 48 degrees? So this is telling us the temperature. We can plug it in for T. Then right here we're dividing both sides by that 8 to get the square root by itself. That way we can square both sides to get the answer. Alright, multiply, divide, and simplify. Rationalize if necessary. Key concept, multiplying with same indexes. You can multiply those radicands together and then simplify. This one here, although they don't have the same indexes, so I can't multiply the radicands, it is simplifiable because the cube root of 27 is a 3. 3 times square root of 3 takes us here. Alright, this one I kind of broke it up into the individual pieces, which you can do if you like viewing it from that perspective. 625 to the 4th root is a 5. 4th root of u to the 5th, a group of 4 would make it out, leaving 1 left over. And then here, v to the 8th, coming out, takes a group of 4 to escape, can make it out twice. Put those back into the proper order, and there you go. On this one, multiply those radicands first to reach to this face. 750 has a perfect cube root in there of 125, which cube roots down to a 5. The 6, however, will remain. Then the cube root of x squared, not enough to make it out, it will remain inside. That's where this 6 and x squared are coming from. Now, y to the 3rd power made it out once. Z to the 6th power, that root sign would extend over to the z, would make it out z squared. So leaving that 6x squared on the inside with the cube root, don't forget to write that cube root, you would get that answer there. Okay, on this one you multiply the radicands, and then you square root, and there you go. This one, do the division first. When you take care of the division, you get the 4th root of 81 over k to the 4th. 81 is the perfect 4th root for 3. K to the 4th, perfect 4th root for k. There you go. On this one, when you divide, you get 9x squared over y squared. All of that's square rootable to get 3x over y. This one here is rationalizing. This is an index of 2, so I want this 3 to the first to get another first power. That way when I multiply these together, I can get the square root of 3 squared, allowing that 3 to escape. Okay, so once we do that, we then have in the denominator 5 square root of 9, or 3 squared, if you want to view it from that perspective, over top of 6 square root of 6x. All right, and then this is a 3. 3 squared, square root of that is 3. 3 times 5 is 15. However, on my answer key, this can continue to be simplified, dividing both of those by 3 to get 2 square root of 6x over 5. All right, and this does extend over the x. All right. Adding or subtracting if possible. In order to add, you have to have the same index, which we do, and the same radicand, which we don't. So this one cannot be simplified. On this one, same index, same radicand, so essentially all we're doing is changing the coefficients. I've got 1, I'm losing 2, takes me to a negative 1. Notice that that square root of 3x stays the same. It's our, essentially you could think of it as a variable. This is no different than 1x minus 2x to get a negative 1x, except just pretending that x is really square root of 3x. So it's just like adding up apples and oranges or like terms. On this one here, initially it looks like they will not be able to add together because they have different radicands, but if you simplify it first, you see that they will. 32 breaking down into 16 and 2, square root of 16 giving us a 4. There's already a 3 out there. 3 times 4 gives us the 12. Breaking down the 50 into 25 and 2, square root of 25 is 5. 5 times the 2 in existence gives us the 10. And then now they both have that same radicand of square root of 2. So I can add the 12 and the 10 together. This is essentially saying I have 12 green balls and 10 green balls. Add them together to get 22 of that same unit. All right, this one's the same concept. None of them look like they're going to be the same, but by the time we simplify them, they all end up having the same radicand, and they're all square roots, so they all have the same indexes. And then we're focusing in on 12 minus 6 minus 12, because all of them have the same square root term with them. So we interact the coefficients and land at negative 6 square root of 10. All right, so on this here, important thing to remember, regular numbers multiply like always. Numbers on the outside multiply with numbers on the outside of square roots, and numbers on the insides multiply. So as we FOIL this out, you can see the different terms. We've got the 2, got the negative square root of 5, negative 2 square root of 5, and then this 5 came from the square root of 25, which turned positive because of negative times negative right here. Positive square root of 25 is a 5. 2 and 5 give us this 7. And then you interact this. This is negative 1 minus 2 to get that negative 3. All right, so this one, when you square it out, don't forget to write it out twice. And then you FOIL. Square root of 2 times square root of 2 would be square root of 2 squared, which is just a 2. Now remember, when you're multiplying these, multiply those inside numbers. 2 times 7 is 14. Then we have another 2 times 7 is 14. Then we get a 7. And if I have 2 of something, that's what it would look like. 2 square root of 14. 2 and the 7 to get the 9. Alright, so here on this one, the middle terms end up canceling out on this one, which you hopefully recognize because you had the same terms, but a plus and a minus for the to be conjugates there. And you can sort through, it's color-coded. And you can see why those middle terms cancel out by following the colored arrows. And it ends up just being a constant because conjugates always get those square root terms to cancel out. All right, 6.4. write its expression in simplest form. Assume that all variables are positive. That's just a stipulation that I have to toss in there. All right, so in this is no different than same base, add the exponents. This would just be like x squared times x to the third to get x to the fifth. Add those exponents up, you just get to the 7th power. This one here, we need to switch it into square root form and then realize same indexes and we're multiplying. We can multiply the radicands, and then 225 ends up being a perfect square for 15. This one here. This negative tells us to take the reciprocal, which is why we took this entire problem down to the denominator. All right, and then we multiplied in. So this would be 1/3, 8 to the 1/3, and then 15 times to the 1/3. Or you could think of this as being everybody to the cube root, because that's what everybody to the 1/3 power would be. You could think of it as everyone to the cube root, which then cube root of 8 is 2. Cube root of x to the 15th power is x to the 5th. All right, so here, regular numbers multiply like always. Then we have same base, add the exponents. All right, and then you had the option here to leave it in exponential form or changing it over to root form, which would look like this. Index of 6, x to the 7th, pulling out one group of 6 and leaving 1x left over. Either one of those answers would work. All right, this one here we have to do division. So on this here, 12 over 4 is 3. And then we have same base, but in the numerator and denominator, which has us take the top exponent and subtract the bottom exponent, which we can see happening there, giving us y to the negative 1/6, which tells us to take it down here to the denominator. All right, or you could think of it as the 6th root of y. Now, really, we need to keep going with this one in terms of rationalizing by introducing 6th root there, a y to the 5th to match up with that y to the 1st. Then when we multiply here, we get the 6th root of y to the 6th over top of 3, 6th root of y to the 5th, and this is just a y. So the final answer here would be that numerator, and then that denominator of y. All right, so let's check out this one here. This is power to a power. Remember that 3 has a 1 with it, and this 2 has to multiply by all of the exponents. When we do that, we'll get 3 squared is 9. And you can see those following exponents, and you could leave it in either exponent form or radical form, so this should be a b. Should be a b there, because it was the b to the 2/3 power. All right. This one, I went ahead and distributed the 2 first before I dealt with the negatives. So I multiplied every exponent in there by 2, even this invisible 1. And then I did the various rules. For the x there, I did the top exponent minus the bottom exponent. When I did that, I got x to the negative 2, which means I'm going to have to move it to the denominator. And then for the y's, what happened here was y to the negative 1 is really a y in the numerator to the 1st power. Same base, add the exponent. All right, so let's start to... All right, now in this video here, and we'll pick up on 6.5 in the next.